Okay, so now in chapter 19, we will discuss and talk about functions. Previously, actually, we are doing a course on Introduction to Pure Mathematics by using a book named A Concise Introduction to Pure Mathematics by Martin Lebach. So let's talk about the functions now. So in much of the mathematics, and it's everywhere in the mathematics and the study of mathematics, we have to encounter in some sense about functions. So in this chapter, we give the definitions and some elementary examples and introduced certain important general types of functions. So let's start with the definition. We say that let S and T be sets a function from S to T is a rule that assigns signs to each element of the set S a single element of the set T. We denote it by f of S, and this f of S will be an element of T. Then we write that this f is a function from S to T. Okay. To mean that f is a function from S to T, if f of S is some small t, we say that f send S to T. F sends S to T. Now, if f from S to T is a function the image of f is the set of all elements of T that are equal to f of S for some element S in S. We write that f of this capital S for the image of f. So thus, f of this capital S is going to be a set which contains all the f of S such that S is an element in the capital S. Okay, perfect. So that's how we talk about the image. And all of the elements inside the set S are domain, is the domain of the function f. Okay, let's give some examples. So 19.1. Number one is we define that f from 1 to 3 is set to the integers by just squaring the elements of the first set and subtracting 4 for x in the set 1, 2, 3. Then the image of f is f of is the set which is -1, 0, and 5. Okay, you can say that because f of 1 is 1 minus 4. F of 1 is 1 minus 4. Sorry, this should be -3. My bad. And so this is -3. And then we have f of 2, which is 2 square minus 4, which is 0. And f of 3, which is 3 square minus 4, which is 5. Okay. Number 2, we have a function from reals to reals by f of x is x square for all x in R. The image of f is, if we apply this f on R, we will get that f of x such, we will get y, given that y is also a real number, or we can more explicitly say that f of x is y, given that y is also a real number and y is greater than or equal to 0. Right. So apparently we are saying all the positive reals. Yeah. Okay. Number 3, we say that a body is dropped and falls under gravity for 1 second. The distance traveled at time t is 1 over gt square. If we call this distance s of t, if we call this distance s of t and write I is a set which contains t from the reals such that t is between 0 and 1, then the small s is a function from the set I to the reals defined by s of small t is 1/2 gt square. The image of this s, the image of this function s is the set of reals between 0 and g/2. Perfect. Number 4, let's define a function from n cross n to the integers by taking 2 by and other pairs as m minus n for all m comma n in the naturals. The image of f is z. The image of f is the set of integers again. We can define the 5th one. We say that we have a set which has a, b, c as elements. Then we can define a function on this set s to s. And we can define another function from s to s as follows. So f sends a to b, b to c, and c to a. G sends a to b, b to c, and c to b. Okay. Then we say, then the image of this function s, the image of function f is set s, while the image of function g is only the elements b, c, because none of the elements are sent to a by g. Okay. In the same context, let's give another example and let's talk about something important. Let's say, let S be any set. And we define a function that is defined like this from S to S by that so it takes, or I should say x for all x in S, and this function is called the identity function of S. Okay, so let's now define the types of functions. Right. Definition. We say that let f is a function from S to t. Let f be a function 1. We say f is onto, or the other name is surjective, if the image f of S is nothing but t, i.e., if for every small t in t, there exists small s in S such that f of small s is small t, means that every element of t should be mapped by some element of S. Okay. 2, we say that, say f is 1 1, or the other name is injective, if whenever for any two small elements, or any two elements of the set S with both distant elements, x1 is not equal to s2, then f of s1 is not equal to f of s2, or in other words, f is 1 to 1 if f sends different elements of S to different elements of T. Another way of saying it, another way of putting this is to say that for all S1, comma S2 in the set S, we have f of S1 is f of S2, then S1 should be S2. So this is how we use to check whether the function is 1 1 or not. Number 3, we say f is a bijection if f is onto and one-to-one. In other words, or surjective and injective. Okay. Now we have defined 6 examples for the functions above. Let's find out which of them are of which type. So example, check which functions in example 19.1 have which types, are of which type, are of which type. So the function one, f sends 1, 3, 1, 2, 3 to the set of it was a function number one was a function from this to send integers, by the rule that f of x is x square minus 4, and you can see that since 1 to -3, 2 to 0, and 3 to 5. So if you check for the first one, it's not onto. If you check for the second one, every element of the domain, like every element of S, is sent to some different element of S, of Z. So it is surely 1, 1. And it is not onto, so it can't be bijective. So it is 1-to-1. But not onto, because f of 1, 2, 3 is not Z. Okay, perfect. Number 2. So number 2 is, number 2 says that f is a function from R to R f of x is x square. Okay. So again, is not onto, and it is not 1, 1 either. Since so it's not onto. Why? And 1, 1. Let's say it's not onto. Why? Because the range of this function is going to be f of x is equals to y, where y is a real number and y is greater than or equal to 0, which is clearly not all of the real numbers. So not onto. Second, f of 1 is 1, f of -1 is 1. So not 1-to-1. 3. Number 3 is the function which is s of t is 1 over gt square, where s is a function from I to r. Yes. Now you can see every time you take a different time, you will get a different answer. And every time you took a same time, a y is dropping at the same time, you will get the same answer. So you can say by saying that it is 1-to-1, since you can prove that for t1 comma t2 in I, you say that s of t1 is s of t2, which is nothing but, then we can say 1 over 2 gt square 1 is equal to 1 over 2 gt square 2. That is giving you that t1 is t2. Also, s is not onto, because f of I is not equals to r. Okay. Number 4. Number 4 function is that we are taking the outer pairs from natural numbers and sending them to integers by the rule that we take m comma n from there and we get their subtraction. Okay. Now see, number 4 is not onto, but it is 1-to-1. So not onto, because surely you will never get this equals to z. Sorry. Oh, sorry. My mistake. This is equals to z. Why? Because if you take all of the integers, all of the natural numbers, and then you subtract them, eventually you will be getting this. So this is onto now, but not 1-to-1, since for 1 comma 1 you get what? F of 1 comma 1 is 0, and for 2 comma 2 you again get f of 2 comma 2 is 2 minus 2, which is 0. So not onto. Number 5. Number 5 is a function. So we have a set A, B, C. We have a function f from S to S. And f of A is B. F of B is C. And f of C is A. We have another function which from S to S, which is f of A is B, f of B is C, and f of C is B again. This is the example number 5. So the function f is a bijection is f of s is again s. You're getting everything back. And f of a is not equals to f of b, and which is not equals to f of c. A weird way of showing it is one-to-one. So onto, so one-to-one. But G is neither one-to-one nor onto, because f of s is not completely s, so not onto, and f of a is f of c, but a is not c, so not onto, so not one-to-one, not onto, not one-to-one. Okay, perfect. And identity function is again a bijection. Okay. I'll end it here, and then we will discuss some other properties of the functions in the next one.